All right, so let's just take a look at some of these vector problems. We got a ship heading due west at 15 kilometers per hour, and we have a current running due south at 3 kilometers per hour. And we want to know the velocity of the ship relative to the seabed. So to do this, we need to add up these two vectors, so that's going to be here. It actually turns out the way we can combine these vectors, since I only have a horizontal going to the left and a vertical going downwards, I can treat these as the components of a triangle. So if I were to do the head to tail addition thing, I could take the 15 here, and then the 3 here, and then my resultant vector will be the hypotenuse, which goes from here to here. So to actually get that total velocity, that's going to be 15 squared plus 3 squared, all under a square root. When I work that out, just throw that in mind. So I'm going to end up getting here, it says 15.3, but I suppose since we're doing this as IB physics, this would actually work out to be 15 when we get the answer. I should have been more specific. I should have said 3.0 just so I can keep 2 sig figs. Sorry about that, because we'd probably round this to like 20, which I don't like to do. Now, to get the angle here, that'll be at an angle of, we want to take the inverse tangent of 0.2 because that's 3 over 15. And when I actually get that inverse tangent, it'll be, again, just working with this here. Sorry for the delay. There we go. So the inverse tangent of 0.2 works out to about 11 degrees. So 15 kilometers per hour at 11 degrees. Right. Now for number 2, we've got a couple of tractors pulling. This is just great. One tractor pulling 3,000 to the west, which is to the left. And then the other is with a force of 2,500 newtons in the direction 255 degrees. So what we're basically saying is, I don't know why it says 2,500 newtons at 225 degrees. So to be clear, this label here, you know what, let me just draw this a little bit differently. Here's what I want to say. I've got one force, 2,000 newtons, going this way. And then with respect to 0 degrees, I'm saying I've got at 255 degrees a 2,500 Newton force. So here's how I'm going to do this. I've got force 1, which I'm going to say is 2,000 at 0. When I want to express this in x and y coordinates, 2,000 cosine of 0 gives me 2,000. And the y component is going to be 0. And then I have F2, which is 2,500 at 255 degrees. Look how I write this in terms of x and y. That's going to be 2,500 times the cosine of 255, comma, 2,500 times the sine of 255. And I can put that into my calculator. And what I'll end up getting is negative 650, comma, negative 2,400 newtons. I'm just keeping it to 2 sig figs is what I'm getting. So I actually got 2,414. So now when I add this up to get the resultant, I have F1 plus F2. So I'm going to combine this and this. When I combine those, I'll get F1 plus F2. And that's going to give me 1,000. Actually, this is negative 2,000 here since it's to the west. This is going to be negative 2,650, comma, negative 2,400. So let's get the resultant vector. the length of the resultant vector, I'll call that FR for resultant. I'll actually use Pythagoras' theorem for that. That'll be the square root of 2,650 squared plus 2,400 squared. And that's given me 3,600. It's actually a 3575 when I'm rounding to 3,600. And the angle is going to be the inverse tangent. Let's be careful. Okay, it's in the third quadrant. So I'm going to need to do a fraction here of y over x. So it's going to be the inverse tangent of 2,400 divided by 2,650. And I'm getting, if you put this in your calculator, the angle you'll get will say 42 degrees, which points this way. But let's be careful. We need it to be 42 degrees with respect to this here. So that's going to actually end up being 200, and I could say 22, but let's just do sig figs. 220 degrees. This would actually be 222 degrees when we actually get this answer. So that's the resultant force. So that's questions 1 and 2.